Hello, my dear students. Welcome to the today's session on one of the most interesting chapters of 11th class, chemical bonding. In our yesterday's class, we understood what is meant by a chemical bond and what are the theories we have to learn except crystal field theory this year. So today we will start the first theory, that is Kossel-Lewis theory. Kossel-Lewis approach to chemical bonding. These two are the scientists, Kossel and Levies. Kossel from Germany, his area of study was biochemistry, whereas Levies from America, his subject was physical chemistry. Okay, so separate, special, it depends upon the specialization. So these two scientists were the first to give the concept of chemical bonding. Okay, further, now today it is modified, but still we have to take the base from the Kossel-Lewis approach. So let us start Kossel-Lewis approach to chemical bonding. This he gave in the year 1916. So in 1916, Kossel and Levies succeeded in giving successful explanation based upon the concept of electronic configuration of noble gases about why atoms combine to form molecules. That means among all the electronic configuration of up to 92 elements, that is uranium, they were concentrating only on the noble gas. Why? Let us study this next point. Atoms of noble gases have little or no tendency to combine with each other or with atoms of other elements. These noble gases, they are chemically least reactive. Not only they react with themselves, they don't react with themselves, but with other elements also they say no to react. Why? This means that these atoms must be having some some different type of electronic configuration where this type of configuration is not there with any other atoms. That means this means that these atoms must be having stable electronic configuration. Other elements, they don't have this is stable. Here, what is meant by stable electronic configuration? Let us see. Due to the stable configuration, the noble gas atoms neither have any tendency to gain nor lose electrons, and therefore their combining capacity or valency is zero. Sometimes for 1 mark they will ask why the combining capacity or the valency of noble gases or the group 18th members is zero, because they don't want to combine at all. When they don't want to combine, then combining capacity is zero or valency is taken as zero. They are so inert that they even do not form diatomic molecules and exist as monatomic gaseous atoms. See, they are so lethargic, they are so inert that even with themselves, helium He2 and argon Ar2, how we have O2, N2, H2, like that we don't have Ar2, He2. Why? They will not react with themselves also, because both are inert, both are inactive, both are chemically least reactive. So they exist as monoatomic gaseous atoms but not as diatomic, more than one. Okay, because of their least chemical reactivity. Why they show chemical least reactivity? Because of this special electronic configuration what they have. This type of configuration is not there with any any of the atoms on the modern periodic table. You see, helium only one s, it is completely packed, whereas neon full packed. All everything is packed, only fully filled. So all these from neon to radon, they follow octet rule. What is octet rule? Having 8 electrons in their outermost shell. See, 2s, 2p are the outermost orbitals, and electrons present in the outermost orbitals are valence electrons. So 8, 8, 8, 8, 8. except helium, which follows the duplet rule. Okay, there are two rules. One is duplet rule, other one is octet rule. What is duplet rule? Duplet rule is only one K shell, and that too it is full. It is chemically least reactive. It is example is only helium. Whereas other inert gases, they have octet rule. They follow octet rule, having 8 electrons in their outermost shell. It is known as what? Octet. So that means why they are most stable? Because of either duplet or octet. Now, because duplet is only one case, no, so we will not highlight that. So we will go to the most important rule known as the octet. Oct is stands for 8, having 8 electrons. All atoms other than noble gases have less than 8 electrons in their outermost shells. I told you, no, except noble gases, except inert gases, except members of 18th group, all other atoms they have less than 8. In other words, the outermost shells of these atoms do not have stable configuration. Then what is the conclusion? Conclusion is we have already concluded that noble gases have stable electronic configuration. If this system is not there with other atoms, then other atoms are not stable. Therefore, they combine with each other or with other atoms to achieve stable noble gas electronic configuration. When other atoms they don't have this type of configuration, they want to achieve that type, because in the nature it is branded as noble gas configuration is the best and the stable electronic configuration. Other atoms they don't have, so they want to go for that best and the stable configuration. So to go to that, either they have to lose or they have to gain or they have to share. They have to do something. That's why other atoms wants to have noble gas configuration. So in doing so, they want to lose. They want to go for the chemical combinations. These elements undergo electronic rearrangements to attain stable noble gas configuration. Same thing he told. Therefore, conclusion. The tendency or urge of atoms of various elements except noble gas to attain stable configuration of 8 electrons in their valence shells is the cause of chemical combination. Why elements will combine, why chemicals will combine? It is because what? They want to achieve 8 in their last shell. That's why they want to combine. So this is the reason, this is the cause for the chemical combination. This is the reason for the bond formation. And the principle of attaining maximum of 8 electrons in the valence shell of atoms is called octet rule. Now we have concluded what is meant by octet rule. Why they go for the chemical combination? Because of having 8 electrons, and having 8 electrons is called as what? Octet rule. Nice. Levies introduced simple symbols to denote the electrons present in the outer orbit of atom. These electrons are known as valence electrons. So to show the chemical combination, Levies made an attempt to show the outer electrons in the form of a cross, in the form of a dot, in the form of some different symbols, and they are known as what? Levies structures, or the Levies dot structures, or the Levies symbols. These symbols are known as electron dot symbols, and the structure of compound is known as Levies dot structure. One example, see carbon, atomic number 6, 1s2, 2s2, 2p2, outermost 2s2, 2p2, because 2s2, 2p2's principal quantum number is 2 only. So together they belongs to second shell. So they are taken as outermost electrons, and the valence is 4, and the 4 is here, 1 electron, second electron, third electron, fourth electron of the carbon. And what are these? Each hydrogen has given 1 electron to the carbon because they want to go for combination. So hydrogen having only 1 electron, they want to achieve like a helium. So helium. Now carbon is what? 1s2, 2s2, 2p2, 2p4. So it wants 4 electron. So 4 electrons are taken by the carbon from the four different hydrogen atoms. So thereby this also will acquire the stability by going for helium structure, and this will go for the what? next nearest noble gas 8, that is neon. So both will acquire noble gas configuration, both are happy, and chemical bond is formed and the chemical compounds are formed. In the same case, you can take water example. Water atomic water is formed by the combination of O and the H. Okay. Now, if you see the O, what is O? Atomic number of O 8, 1s2, 2s2, 2p4. Okay. So outermost is 2s2, 2p4. 6 electrons. It wants 2. It wants 2 electrons. Okay. So those 2 electrons are taken by 2 hydrogen atoms. So one from the oxygen, one from the hydrogen, bond is formed. One from the oxygen, one from the hydrogen, and bond is formed. These are what they will. I told you in the previous yesterday's class. They help. They remain. Slight repulsions are there, but they cooperate for the chemical bonding. So this is called Levies structure for the water. Levies structure for the methane. In the same way, we can draw Levies structure for many atoms and many molecules. For example, please see. I have driven and arranged the Levies structure for the first 20 atoms. Kindly go through. And this is what Levies structure for the carbon tetrachloride. Carbon wants 4. Okay, wants 4. Chlorine 1s2, 2s2, 2p7. 1s2, 2s2, 2p7. Chlorine is what? Chlorine having 7 electrons. So it want 1 electron. So 1 electron from the chlorine, 1 electron from the carbon, they go for the bonding. Okay. And here also 1 from chlorine, 1 from carbon, 2, 1 from chlorine, 1 from carbon. So like that they go for the bonding. And you see here whether octet is achieved or not. See here 1, 2, 3, 4, 5, 6, 7, 8. So these 2 electrons are taken for the carbon as well as for the chlorine. So around this 8, around this you see 2 plus 2 plus 2 plus 2, 8. Around this 8, around this 8, around this 8, octet is completed, stability acquired. So using the bond line, it is shown like this, either in this form or in this form. In the same way, we can show silane. Silane is like a methane. What is methane? Methane is CH4. Carbon and the silicon are the members of the same group, that is 14th. So carbon with hydrogen, 4 hydrogen, methane. In the same way, silicon with hydrogen, silane. Like that name is kept. Silicon wants 4 electrons. Okay, and 4 electrons from 4 different hydrogen. Hydrogen acquired duplet, 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 whereas silicon acquired the octet. All are happy. So either they have to go for the duplet or they have to go for the octet. Ultimately, they want stability and the bond is formed. So I think we have studied few examples for the Levies structure and the Kossel-Lewis approach. And tomorrow we will go for some other structures and some other points on the Kossel-Lewis theory. Thank you, my dear students.